is a very important concept in biochemistry, which is why we kind of like jump in right in the beginning with all that math. It's not because we're trying to be mean, it's just that understanding pH and the relationship between pH and whether things are protonated or not, whether there's free protons hanging around to catalyze reactions. All of this is really important, and to know all of this, we need to basically know these equations, know how we can do things like figure out what the pH of a solution would be if you were to dissolve a weak acid or a weak base, do things like figure out how we can control the pH by making buffers that have almost equal amounts of conjugate acid and conjugate base, so there's enough base there to mop up any acid and enough acid there to mop up any base. To do things like predict how the pH would actually change if you were to add a strong acid or a strong base to that buffer you made. It can also allow you to do things like predict whether reactions are going to go faster or slower if they rely on having a certain amount of protons around. So there are lots of different reasons why pH comes into play, and there are a bunch of different types of calculations that we can do to figure out various things about the pH. So here are some work through examples for these. Start off with an overview of the different types, and then I will break up the rest of the video into smaller parts as well and post those individually. So if you want to jump just to one certain question type, you can go ahead and do that. But let's just dive in. The best way to learn acid and base equations is really just to practice them, but it can help to have some examples and a kind of overview as to the types of problems that you might be encountering and strategies for approaching each of them. Then you can go ahead and try a bunch of practice problems, and don't worry, you'll get a lot of practice in class. So let's go over the four kind of main types of problems, and then I'll go through how we can think about each type. The first type is going to be the simplest. And in this type, what you have is you have some sort of acid, and you're going to dissolve it in a solution. And when you dissolve it in a solution, some of it's going to dissociate. So some of it is going to deprotonate. And then you're going to be able to calculate what proportion deprotonated, what's the concentration of the deprotonated versus and the concentration of the protonated form, so the conjugate base and the conjugate acid, and what's the pH of the resulting solution. You'll also be able to do problems where instead of just dissolving your acid in water, you're actually mixing it with the base and then seeing what happens. Now you could be asked things like, what's the concentration of each of those acids and bases, both their conjugate acid form and the conjugate base, as well as what's the pH of the solution. So an important point that we're going to be coming back to over and over is that we have an equation called the pKa that's going to tell us about the strength of an acid, and that's going to be a constant. So our pKa is not going to change, but the pH of the solution can change depending on the concentration of our acids and of our bases. And so we'll see how that's going to affect things, how that can be altered in different conditions. Speaking of altering that pH, so remember that the pH is going to be dependent on the proton concentration from all sources. So this is the source of the acid that you dissolved. In the simplest case, the only source of the protons is going to be from that acid you dissolved. But in other cases, you can have acid from multiple acids going on. And especially one thing that we often do in the lab is we take a solution and we are going to adjust the pH of that solution. Or maybe in your bodies, you have a molecule and like an amino acid, and you want to figure out, okay, well, what proportion of it is protonated or deprotonated? But that amino acid isn't just the only thing in that solution. Instead, there's lots of other things. There's lots of other acids that are contributing protons. And so the pH is going to be different. But using this equation, this Henderson-Hasselbalch equation, you'll be able to calculate the proportion that is protonated or deprotonated. And if you know volumes and stuff, you can calculate the actual moles, the quantities. In the lab, what we're going to be doing, and you'll get lots of practice of this buffer calculations in the lab, is basically you want to make a pH buffer. So basically a combination of a weak acid and its conjugate base that is designed, like you titrate it, basically you want to get it at the concentration of your acid and your base where it's at a pH that you want it to be at. So remember that the pH is going to be dependent on the amount of the proton availability.
Now we'll see in the first type of problem that if we just dissolve an acid in water, we're going to reach some sort of equilibrium and we're going to have a specific pH, and that pH is going to depend on the concentration of that acid or of the acid that we add, as well as the pKa of that acid. Those are going to determine what the pH is going to be. But that doesn't mean that we're stuck at that pH. So we'll have some initial values, some initial ratio of products of our acid and our base. But then if we, and we'll have some initial concentration, therefore, of our protons and therefore our pH. But if we add an external acid or a base, then we can shift that pH. And then if we shift the pH, well, now we are going to change our concentrations of our acid and our base, and then we can calculate that as well. These are going to be more complicated calculations, and so we're going to use this thing called an ICE table. Some of you might be familiar with an ICE table, maybe from your general chemistry class. But basically what you do is you take your initial concentrations, then you take the change into concentrations, and then you use that to calculate the difference at equilibrium. And so we're going to be stressing this point a lot. Equilibrium. When we talk about our Ka, in our pKa, this is going to be at equilibrium. So basically, you would dissolve your acid in water, you let it mix, and then eventually it's going to reach an equilibrium, and that's where you want to calculate things. Now, initially, say you add an acid or you add a base or something like this, when you have this change, you're perturbing the system. So you might have some initial equilibrium in the case of those hardest problems, or you're just going to be dissolving something in the case of the easiest problems. But you can think of having some sort of equilibrium or some sort of initial conditions. And then you're going to perturb that and then reach a new equilibrium. And when you reach this equilibrium, this is when you're then going to take into account your Ka, because that's an equilibrium constant. For any reaction that's at equilibrium, we can write an equilibrium constant that's going to be equal to the concentration of our products over the concentration of our reactants. And instead of just simply adding together if you have multiple products, instead of just adding them together, you're actually going to be multiplying them. And same with reactants. So, and if you had stoichiometric coefficients, you'd be raising them to the coefficient. So go ahead and review your chemistry book and notes and all that good stuff to refresh your memory of these equilibrium constants. But you can do this for any sort of reaction, including the dissociation of an acid. And so when we do this for the dissociation of an acid, then we call it our Ka. So our Ka is going to be equal to the concentration of our conjugate base times the concentration of protons divided by the concentration of our acid. And we typically abbreviate this generic acid HA and its conjugate base A-. And then we can write this as H+, or what I typically do is I like to write it as H3O+, because what happens is that we're having this happen in an aqueous solution. So we're going to ignore the actual water because it's such a high concentration. We can consider that it's not changing. But we do want to consider the fact that we have all the protons, and the protons, instead of just hanging around freely, they're going to be latching on to a water molecule. And so we get this hydronium ion, but you might see it written, so you'll see it either written as a hydronium ion or just as a proton H+. Now, so this would be the Ka, but typically what you're actually going to be seeing is the pKa. And so the pKa is the negative log of the Ka. It's similar to how the pH is going to be the negative log of the hydronium concentration or of your proton concentration. So that little p just indicates you're taking the negative log. Now, with mathematical rearrangement, if you have the pKa, you can calculate the Ka, and if you have the Ka, you can calculate the pKa. So if you need to calculate the Ka, because you're typically given the pKa, that's going to be what can be measured and what you can find in like a table, say. You can get those for different acids, and the stronger the acid, the lower the pKa is going to be. because that's going to mean that it has a higher Ka. So more dissociation, higher Ka, and therefore, because of this inverse relationship, it's going to be a lower pKa. And so another way to think about this is the pKa is going to be the concentration at which the pH at which half of it is protonated and half of it is deprotonated. If you have a lower pKa, that's going to mean that you need to get to a lower pH. You need to get to more extreme conditions in order for half of it to still be protonated. And so under typical conditions, most of it is going to be deprotonated. And so we'll get into examples of all of this. But basically, if you're above the pKa, then you're more than half of it is going to be in the deprotonated state, because remember, that's higher pH, lower H+ concentration. So there's lower protons around to pick up, and therefore you're less likely to be protonated. And the lower the pKa, the less likely you are to kind of take one of those protons and hold on to it if you run into it. So we'll see much more examples of this throughout the course. So that was the Ka and the pKa in the pH. And you can actually combine all three of these, and we'll see that we can do this using something called the Henderson-Hasselbalch equation. So we're going to use this whenever we're perturbing the system. So we're going to use this whenever we're perturbing a system with extra acid or base. So basically, you don't just have that one thing in there. You're going to adjust the pH with something else. So you're kind of adjusting, maybe in the lab, you're adding an acid or a base, or in your body, you have a solution already at a certain pH, and then you want to say, okay, well, this component within it, what is the proportion of it that's protonated or deprotonated, given that it's in this environment at a certain pH. And so those are going to be the cases in which we'll be using the Henderson-Hasselbalch equation. And we'll look at an example of how we can do that. And then we'll be going over some ways in which we can use this to, say, figure out what proportion of an amino acid is protonated or deprotonated at a given pH, given its pKa. So we'll be doing lots of that. And then finally, there's this equation that we're going to use when we're mixing an acid and a base that can come in really handy. Basically, it just comes from rearranging all this stuff. And you can figure out that KEQ is also equal to 10 to the power of the pKa of your products minus the pKa of your reactants. And so we'll get an example of that in a minute. But let's start off by just going to our simplest example. And this is also going to help us understand where that Ka and where that pKa come from. So in this simplest example, you're going to dissolve an acid in water and see what happens. So once I say see what happens, you could be asked, like, what's the concentration of the acid and the base, and what's the pH of the solution? Now, when we talk about concentrations, when we do our calculations, we're typically going to be doing these in molarity. So this is going to be typically in terms of molarity. We'll see later that we might have to work in terms of moles for some of the problems if we need to consider a changing volume. But for these simpler ones, we're not going to worry about that, and we're just going to be dealing with in terms of molarity. And then if you're given the volume, you can calculate actual moles. Okay, and then the pH of the solution. So the pH is going to depend on the proton concentration, which is going to be one of those products from the reaction. So let's go ahead and sketch out what this reaction is actually going to be. So we're going to start, and we're going to have our acid. And we're going to take our acid. What color should I be? Okay, so we're going to take our acid. We have some acid, we have HA. Remember, that's just our generic acid. And we're going to go ahead and we're going to add it to water. Now, some of it's going to deprotonate, and that's going to give us our conjugate base, as well as that proton, which is going to grab onto a water and give us this hydronium ion. And this is going to be a reversible reaction, so it's going to be going back and forth in each direction. and it's going to equilibrate over time. So give time and will equilibrate. So it's going to find its happy place, and its happy place is going to be characterized by its Ka, or we can also think of it as by its pKa. Remember, the pKa is just going to be the negative log of that Ka. So what's happening when this acid dissolves? Well, we're going to be losing some amount of the acid. So some quantity of the acid is going to be dissociating. And we can represent this, no matter, we don't know what it is right now. Right now, we're just talking in generic terms, but we can represent it as some variable X. So some variable X is going to get removed. And that when you lose X amount of the acid, well, now you're going to gain X amount of the base, the conjugate base. And you're also going to gain X amount of that hydronium ion because you've basically lost it, given it to a water, and given it to make this H3O plus. So now technically this is going to take away a water molecule. But the thing is, we're just going to ignore the water. Because the water is such a high concentration, we're just going to ignore, and we're going to take it as a constant. And we're going to take it as a constant that's going to be kind of accounted for in all of our calculations, so we don't need to worry about this. And so why is this a valid thing to take as a constant? Well, if you think about the water concentration in cells, or water concentration in water, it's basically like 55.5 molar or so. So this is going to be super high concentration. And we'll see that when we do these equations, they're only even going to be valid at dilute solutions. So we're not going to be talking about anything that's even like a molar. That would be a high concentration considered. And we have water is going to be about 55.5 molar. So anything we do to change that water concentration is going to just be a drop in the bucket. And so we're not going to worry about it. And so for now on, we're just going to simplify this reaction as thinking about it as HA associating to give you A minus plus H3O plus. Okay, so that's going to be our equilibrium reaction. And remember, for any reaction that's at equilibrium, we can write a KEQ equation. So we can go ahead and write a KEQ equation, which is equal to our products over our reactants. And in this case, that would be our A minus, or conjugate base, times our proton concentration, all over our HA. So this is our equilibrium constant. And remember that in the case of an acid dissociation, this is also equal to our Ka. So we can say that the Ka is going to equal concentration A minus, H3O plus, all over HA. Okay, so we can write this equation. And now what we're going to do is we're going to plug in these changes, these X variables that we got. And so I'm going to kind of clean up the page a little. So now that we're ignoring the water, let's go ahead and let's rewrite this equation over here. Let's rewrite our A and that sort of thing. Okay, so we have HA over here, A minus plus H3O plus. Now, the first time we're actually going to do this, let's go ahead and let's do an ice table so you can help see where things come from. And then we'll see how we can kind of skip the ice table if we recognize the trends. But then later we'll come back to our ice tables. So if we think about our initial concentrations, if we have our HA, we're going to be given this. Typically, I'm talking about like the typical situation. You could have all sorts of variations of this, but typically you're given that HA concentration because you're dissolving some amount of acid. And when you dissolve it, you're going to get some amount of your base and some amount of the protons or the hydronium ions, but you're starting with 0. So these are going to be 0. So you have your 0 initial, which is going to make things easier in this case. Now what's going to happen is you're going to have some sort of change to your system. And so in this case, what our change in the system is we're going to have X amount deprotonate, which is going to leave us with that same amount of the conjugate base and that amount of the proton, of the hydronium. So these are going to be positive. We're gaining these, and we're losing that amount of the acid. And so now at equilibrium, what we're going to be left with is we're going to have our equilibrium is going to be the given acid concentration minus X. And this is going to be plus X and plus X. And so now what we can do is we can say that, well, we have, this is going to be our equilibrium concentrations, and the Ka, well, that is going to be using the equilibrium equations. So what we can do now is we can do plug into here. So now what we can do is we can take that Ka equation and we can say, okay, so Ka is going to be equal to our conjugate base concentration, which we said is X, times our hydronium concentration, which is also X. And that's all going to be divided by your given acid concentration minus X. And so what you're going to have is this is going to equal to X squared over the given acid concentration minus X. And so we can then do this equation when we have the pKa by recognizing the relationship between the Ka and the pKa. So remember that we can get the Ka is also going to equal 10 to the minus pKa, and that is going to equal our X squared over our given acid concentration minus X. And so in order to actually solve these equations, we're going to have to use the quadratic formula. And I don't know about you, but I am not going to want to use write out a quadratic formula and figure out those solutions if I don't have to. So I'm not going to require that my students do the quadratic equation on paper or something like that. I'm going to go ahead and use Wolfram Alpha. And you can use whatever works for you and your teacher if you're watching this from a different class. But that's going to give you two solutions. Only one of them is actually going to be plausible, and so you'll have to determine which one's going to be plausible. Sometimes it'll be easy because one of them is negative. In other cases, what you'll have to do is you'll have to think about the limiting concentration and make sure that your value is going to not be more than the amount that you actually have to start with. Okay, so now let's do an actual example. So how much acetate forms when 150 millimolars worth of acetic acid is dissolved in water, and what is the pH of the resulting solution? So we're starting with 150 millimolars of acetic acid. So that's going to be our initial. So what we can say is if we go ahead and write out that ice table, and remember that if you don't need the ice table, feel free to skip it if you don't feel like you need it, and go straight to what we were talking about before with this equation. But for now, let's just write it out in full so that we can really see where things are coming from. So we're going to have this reaction where instead of our generic acid and base, we're now going to be talking about having this acetic acid, and it's going to be dissociating into its acetate and the hydronium ion. So if we think about our initial concentration of this, well, we're given that our concentration of our acid is going to be 0.150 because we want to be in molarity and not in millimolars. And then we're going to have our initial concentrations of these are going to be 0. But they're not going to be 0 for long because some of our acid is going to dissociate. X amount is going to dissociate, leaving us with X amount of our conjugate base and X amount of our proton or our hydronium. So our final, once it reaches equilibrium, is going to be 0.150 minus X, X, X. And now we're going to plug those into our Ka equation. And so if we take our Ka, in this case, it's going to be equal to our X from here. So our X from the acetate times the X from the hydronium over this 0.150 minus X. And remember that our Ka, we're not given the Ka, but we are given the pKa. And so in this case, we're given that the pKa is equal to 4.8. And so remember that instead of thinking of this in terms of Ka, if we want to think about this in terms of the pKa, that would be 10 to the minus pKa. And now we can simplify this and put in some actual numbers. So I'm just going to put the, you can do basically x squared over 0.150 minus x equals 10 to the minus 4.8. And now I'm just going to go ahead and I'm going to plug this into my Wolfram alpha and see what it gives me for x. Remember to look and make sure that you have all the your parentheses and stuff that's needed so that it gives you the right answer. Thankfully with Wolfram alpha, it's really nice in that it'll kind of like show you the formatted version. So you can check and make sure you're actually written what it actually thinks you wrote, what you meant to write. In this case, it's going to give me two solutions. So it's always going to give you two solutions to a quadratic equation. So in one of them, the solution is going to be minus 0.0015. Or the x is going to be equal to 0.0015. And I'm rounding, so it actually goes a little more. So if you want to think, these are actually, they are different numbers. So this one would be like 155, and this one would be 153. And again, if you rounded earlier, you get a slightly different answer as well. But let's think about which of these answers is correct. So it's going to give you two answers, but only one of them is ever going to be accurate. In this case, one of our numbers is negative. Can we have a negative number? Can we have a negative amount of something? No. Unless I don't know, are you talking about like dark matter or stuff like that? I don't know. This is not that sort of thing. Instead, it's just a wrong answer. So we can ignore it. And this means that this is our right answer. So right now, we're not in the context of units, but we need to go ahead and think back to what this 0.00153 actually represents. We're talking in terms of concentrations, and here we're talking about our molar concentrations. And so our concentration of our acetate is going to be equal to x, and our x is equal to 0.00153 molar. And let's go ahead and in order to kind of compare it to the amount of acid, let's go ahead and let's think about it in millimolars. If we want to think about it in millimolars, well, we're going to multiply by 1,000, 1, 2, 3 moves of our decimal point, and we're going to get 1.53 millimolar. Okay, so now anytime you do an equation like this, I want you to stop and think about whether the answer is reasonable. So going into this, what would we expect? We have that our pKa of acetic acid is going to be 4.8. This is going to be a relatively weak acid. If something is a weak acid, we wouldn't expect that much of it to be deprotonated if you were to just stick it in water. And in fact, the Ka is going to tell us about how much would get deprotonated if we were to just dissolve it. And when we figured out our Ka, we kind of didn't do it explicitly, but let's go ahead and do that now. Instead of just saying 10 to the minus 4.8, let's go ahead and let's see what this is. So Ka equals 10 to the minus 4.8. And if we do 10 to the minus 4.8, we get 0.1234158. So really, really small. Really small. And what does this mean? This means that not very much of it is going to be dissociated. And so because it's going to tell us that basically our reactants are much favored over our product. So the acid, this bottom part of the equation is going to be much bigger than the top. So we get a really, really small number. We have a lot of, less of it is going to be dissociated. And so if we compare our concentration of our acetate, so 1.53 millimolar, to our concentration of our acetic acid, 150 millimolar, well, now we can see that, yes, this is a lot smaller. This makes sense. So we're about 100 times smaller, 100 times less of our base. So this is all making sense. But we're not done with the problem. We still have the extra question of what is the pH of the resulting solution? And in order to solve the pH problem, we need to know the proton concentration. And thankfully, the proton concentration, we have that as well. So our proton concentration, our hydronium concentration, is going to be equal to X. So we can use this to calculate the pH. And so here, what we're going to be doing is we're going to, I don't want to erase that because we're still going to need that X. We have the same X, but now instead of the Ka and the pKa, we're going to be dealing with the H3O plus and our pH. So we have our pH is going to be equal to log of 1 over X, which is going to be the same as saying 1 over 0.00153. And if you plug this in, then you get that your pH is going to be equal to 2.82. So our pH is going to be 2.82, and we're going to have 0.00153 molar concentration of our acetate and of our protons. So remember that it's this concentration of protons that's going to then be determining the pH. And our pH in this case is going to be 2.82. Okay, just a note that you can also write this as pH equals the minus log of your H3O plus. So it's just a little different ways you can write it mathematically, but both of those would give you the same answer. Let's stop ignoring the water for a minute because it's going to help us understand what's going to happen in the case of a base. We have our water, and it has an ionization and equilibrating. Basically, what you have is that this can dissociate into H plus and OH minus. We've been ignoring water, but now let's think about it a little more explicitly because it's going to come into play when we're talking about bases. And it's always coming into play, we're just not really thinking about it. But we have to think about it a little more explicitly when we're thinking about our bases. What we have with water is it's also going to be ionizing to give you H plus OH minus. Whenever we have a reaction, remember that this is equilibrium, we can write an equilibrium equation. So we could write an equilibrium equation for this. That would be our proton concentration times our hydroxide concentration over the concentration of water. If we wanted to rearrange this, what we could say is that KEQ times the concentration of our H2O is equal to the concentration of protons times the concentration of our hydroxide ions. Now, the concentration of water is so crazy high. It's like 55.5 molar that we're just kind of always assume that it's going to be 55.5 molar, and therefore we can lump it in. And we can say that basically our KEQ times this 55.5 molar equals H plus times our OH minus. And then if you were to go and measure this out, what it turns out to be is that this value here, which we'll define as KW, now that KW is going to be equal to 10 to the minus 14 is equal to our concentration of our protons times our concentration of our hydroxide ions. We can take the negative log of these. What we're going to get is that our 14 is equal to our pH plus our POH. So basically, we have this situation where we could think about it in terms of either directly in terms of our concentrations or indirectly in terms of the the pH and the POH. But what this is telling us is that we have this constant relationship where we have a balance between the concentration of protons and the concentration of hydroxide ions. What this means is that if one of them increases, the other has to decrease. So if we see a change in our proton concentration, this is going to cause a decrease in our hydroxide concentration. Now, when we're measuring pH, we're talking about the proton concentration. But when we're adding a base, what we're adding is if we're increasing our OH minus, well, what we're doing is we're indirectly, we're decreasing our proton concentration in order to compensate and keep this constant as a constant. So now let's go ahead and use that knowledge to solve a question about what happens if we were to dissolve a base. So in this case, our sodium acetate. So we need to use a couple of different relationships here. So one is that we've just talked about, that the pH plus the pOH is equal to 14. And the other is going to be that our pKa plus our pKb is going to equal to 14. And so by using these relationships, although we don't know pKb directly, we can figure it out based on pKa of its conjugate acid. So remember that what we have is we have our reaction, equilibrium, H plus A minus. And what we're saying is that when we're talking about our pKa, we're talking about H plus over A minus over HA. When we're talking about our Kb, well, here what we're talking about is the reaction between A minus and our H2O to give us our HA plus OH minus. In this case, so that was our Ka. For our Kb, what we're dealing with is that we have our HA over times OH minus over our A minus. And then remember that again, for these, we're taking the water as being that constant that's going to be accounted for. And so when we do this, basically what we can see is that if we were to solve one of these equations for the other equation and then incorporate the water's equilibration into there, we get this equation where we have pKa plus pKb equals 14. And when we have this relationship, well, now we can go ahead and we can solve for our pKb. Well, we can solve for our Kb, which we can then use to solve for the pKb. So we know that our pKa, the pKa of the conjugate base, of the conjugate acid, is going to be equal to our 4.8. So then we say plus the pKb is going to be equal to 14. And if we do this, we can figure out that the pKb is going to be equal to 9.2. So that's great. And now we can go ahead and we can basically set up the same sort of reaction that we had before. Okay, so here we have something like this. And what's going to happen is that when we add that base, it's going to react with the water. So you're going to lose from this, and you're going to be gaining here. But we're not going to consider the water, remember? So we are just going to we're just going to ignore that water. Now what's going to happen is if we went and we wrote our Kb equation, we would have x times x over our minus x. So that would be our Kb, or our minus 1.150 minus x. And so now what we can do is we can go ahead and we can use that relationship where we have our pKb is going to equal the negative log of our Kb. So it's going to equal the negative log of x squared over 0.150 minus x. And we said that the pKb was going to be 9.2. So 9.2 equals this. And if we go ahead and we go and plug that in and solve for that quadratic. So as always, it's going to give me two answers. And in this case, one of them is negative, so I'm going to ignore it. And the other one, x is 0.0038. Okay, so what is this x? Well, this x is going to be our concentration of our conjugate acid, and it's going to be our concentration of our OH. And if we know the concentration of our OH, well, now we can easily find the pOH. And if we know the pOH, well, then we can find the pH. So basically what we can say is that this is going to equal our OH minus. And now if we want to find the pOH, we just have to take the negative log of that. And what we're going to get is that this value is 2.42. Remember our relationship where that we have the pH plus the pOH equals 14. And so the pH is equal to 14 minus our pOH. And well, we just found our pOH. So what we can do is pH is equal to 14 minus 2.42. And if we go ahead and we work that out, we can figure out that our pH is going to equal about 11.6. Does this make sense? We already expect it to be a high pH, right? Because we're adding a base. And indeed, we have raised the pH, and we have this pH of about 11.6. So you can see that even though we weren't dealing with an acid, we can still calculate a pH by remembering our relationships that our pH plus our pOH equals 14, and that our pKa plus our pKb is equal to 14. Okay, now let's talk about our second type of question. Here, instead of just like dissolving our acid in water, we're actually going to be mixing it with a base. And so we're going to have our acid reacting with the base and leaving us with the conjugate base of the first of the acid, and then the conjugate acid of the base. And we can be asked the same sorts of questions about the concentrations of our acid and our base. But in this case, things are more complicated because we have two that we need to consider. So we have two sets of acid and bases. And then we could be asked the pH of the solution again. And here we have to take into account that we have both those things going on in the solution. So let's go ahead and write out, sketch this out. In this situation, what we're going to have is we're going to have our acid, instead of just writing HA and A minus, because now it's going to get complicated because we have two of them. I'm just going to be writing, start by thinking of just one as the acid and one as the base. Now these are going to react with one another. And again, you're going to reach an equilibrium. And this is going to reach an equilibrium where you're going to have your conjugate acid plus your conjugate base. So remember that this acid is going to contribute to this conjugate base. And this base, well, this is going to be its conjugate acid. But they're going to be reacting with one another so that for each amount of the acid that you lose, you're also going to be losing that amount of the base because these are going to be reacting together. And that's going to leave you with that amount of the conjugate acid and that amount of the conjugate base. Now, in one of these situations, what we're going to be dealing with in this simplest case is that you're starting from zero. You're starting from zero of the conjugate acid and the conjugate base, and you're given how much of the initial acid and base that you're going to have. So what we could do is we could write out our ICE table again. Remember, that's the initial, the change, and the equilibrium. So here our initial concentrations, we're going to be given the amount of the acid, we're going to be given the amount of the base, and then the conjugate, we're going to have zero of each of these. So our change in acid, this is going to be our minus X, our minus X. Then we have a plus X and plus X. And then at equilibrium, we're going to be left with our given minus X and our given minus X and our plus X and our plus X. Now remember that if we have something that is at equilibrium, we can write an equilibrium equation. We can write a KEQ equation. And more specifically, if we have something that is an acid reaction, an acid dissociation reaction, well, then we can write a Ka equation. But in this case, we're going to have the Ka of both our acid and we're going to have the two Kas. So we're going to have two pKas for the individual acid and base reactions that are going on in here. And then we're going to have an overall Ka for the equation. We're going to have an overall KEQ for the equation. And no matter what type of equation that we have, the same thing holds for a KEQ equation. It's going to be our products over our reactants. No matter what type of equation that we're dealing with, it doesn't even have to be an acid dissociation reaction, any type of equilibrium reaction. And so in this case, what it's going to be equal to is our KEQ. It's going to be equal to our products. So we have the X from our conjugate acid times the X from our conjugate base over our reactants. And so we're going to have our given acid concentration minus X times our given base concentration minus X. And this is going to be our KEQ equation. Now, where do our pKa's come into account? We can't just use that pKa and plug it right into this KEQ because we have those two pKa's to worry about. We have the pKa for each of the acids. So remember that when we're dealing with a pKa, so pKa is always for an acid. So even if we're talking in terms of a base, we can talk about its pKa in terms of its conjugate acid. So what we're going to want to do is we're going to want to use the pKa's for this acid and for this conjugate acid. So this is going to take into account the strength of our base by taking into account the strength of its conjugate acid, and then we're going to have the initial acid. And so that's the one we've been used to dealing with the pKa for. Now, in order to combine them for this equation, we're going to use that shortcut that I mentioned earlier. And so you can go ahead and figure out how it mathematically works out. But it simplifies down to KEQ equals 10 times the pKa of your products minus the pKa of your reactants. And so when we're dealing with the products, well, that's going to be your pKa of the conjugate of the conjugate acid. And then your reactants, that's going to be your pKa of your acid, like your initial acid. And so now that we have this equation, we can go ahead and we can rewrite this and we can say, okay, well, we have our 10 to the, and so we have 10 to the pKa of your conjugate acid minus pKa of your acid equals X squared over your given, let me just copy and paste that because I am not very good with writing on this thing. And so I already wrote it once badly, so why not just use it again, badly written. Okay, so it'll be like that, except we can simplify this X times X, we'll just say X squared. And now we have an equation that we can go ahead and we can solve. And so let's go ahead and use this equation with an actual example. And if you wanted to, what you could do is you could write this ice table with your actual values in the example. But I'm just going to simplify things and I'm going to jump ahead and use this formula that we just calculated. And we're going to use this in this following example. The question is, what is the pH of the solution formed when 150 millimolar acetic acid, so that's what we were just dealing with. But now instead of dissolving it in water, what we're doing is we're mixing it with 50 millimolar ammonia. And the question is, how much acetate is formed and how much ammonium ion is formed. So let's go ahead and sketch out what equation we actually have going on, the reaction that we have going on here. We have that same acetic acid, and it's going to now be added to NH3. So this is our ammonium ion. And now what's going to happen is our ammonium ion is going to go and it's going to grab onto that proton, and what we're going to get is we're going to get an equilibrium reaction where we're going to have our acetate plus our ammonium ion. So this is going to be our ammonia, and this is going to be our base, and this is going to be our ammonium ion, and this is going to be the conjugate acid of that base. And then this is going to be our acetic acid, which is going to be our acid, and our acetate, which is going to be our conjugate base. And so now let's think about the numbers that we're going to need. We're going to need the concentrations of our acid and of our base. And so we're given that, so we'll just deal with that when we're with the given numbers. We're also going to need the pKa's of the conjugate acid and the acid. Okay, so the pKa of the acid. We're going to want the pKa of the acetic acid, which we had before and we have again, which is going to be 4.8. Now, we're given two pKa's for the two other pKa's. We're given the pKa of ammonia, and we're given the pKa of ammonium ion. Let's think about what the pKa for ammonia represents. So this is our ammonia. And so ammonia, yes, it can deprotonate. It has 3 protons. It can give 1 up, but it has a pKa of 37. It's very, very unlikely to give this up. What about ammonium? This is going to have a pKa of 9.3. So that is a more reasonable, that's a more reasonable thing. And this is actually going to be the one that we want because we want the conjugate acid. We don't want the pKa of ammonia because that's telling us about ammonia deprotonation when we want to know about ammonium deprotonation because our ammonia is going to be the base in this case. So what we're going to want to do is we're going to want to use this ammonium ion pKa, which is going to be 9.3. Okay, so now what we're going to do is we're just going to plug and chug. So we have 10 times the pKa of our conjugate acid, which is going to be that 9.3, minus the pKa of our acid, which is 4.8. And that's going to be equal to x squared divided by our given acid minus x. So that would be our 0.150 minus x times our given base minus x. So that would be our 0.050 minus x. Simplifies down to 10 to the 4.5 equals x squared over 0.150 minus x times 0.050 minus x. And now I'm going to go ahead and I'm going to plug this into Wolfram alpha. So once again, it's going to give me 2 answers. So x is either equal to 0.0500 or x is equal to 0.1500. So now let's think about which of these is actually right. It's not as easy as before because one of these isn't negative, but we can still figure out which one is correct by thinking about what is our limiting reagent. What do we have more of? Do we have more of the acetic acid or more of the ammonia? We have more of the acetic acid. So our limiting reagent is going to be the ammonia. And we start with 50 millimolars, which is 0.05 molar. Now, if we look at one of these answers, 0.150, that is going to be, basically, that is going to be more than the amount of ammonia that we started with. This is, if we had 0.150 as our x, remember that that's our x is going to be equal to this ammonium ion concentration. And this would be saying that even though we only put 0.05 moles in there, well, somehow we magically ended up with 0.150 moles of it, the protonated version of it, which is not possible. So instead, we can ignore this bigger solution, and this 0.0500 is going to be our answer. And note that it's not like exactly 0.0050, and depending on what you're rounding, you're going to get a slightly different answer. But basically, most of it is going to be reacted, but you're not going to have more reacted than you would have going in. And so this 0.050 is not just our ammonium ion concentration, but it's also the concentration of our acetate. Because remember when we had our ice table, X was equal to both the concentration of that conjugate acid and the conjugate base because the acid and the base were reacting together. And then we can go ahead and we also need to remember our units. So this is going to be molar. Okay, so now let's deal with a solution in which instead of just mixing things and seeing what happens in terms of what does the pH that we reach, let's think about, well, what if we actually go and we alter the pH, say with a strong acid or a base? So maybe you make something in the lab, or you take something in the lab and you drop in some acid or a base, and now you want to see what happens. We're going to be seeing this all the time when we talk about buffers, and we'll talk about in a minute how we can do a more complicated example using a sort of buffered solution. But for now, let's just deal with a simpler situation. But we're still going to be using this Henderson-Hasselbalch equation. So in this equation, now we're saying not only do we need to take into account that pKa, so basically if we were to just mix it in water and let it go, like, okay, what would the pH be? Or even if we were to mix it with another base, what would the pH be? Instead here, we're saying, okay, well, now there's an external source of our protons or of hydronium. And so this is going to alter the pH. So remember that the pH is going to be determined, the pH is going to be the minus log of the proton concentration. And so we're going to have protons that are given both from the initial acid we dissolved as well as from whatever acid we're adding. And so we're going to have to take into account both of those. And then that's going to basically affect the ratio of our acid and our base. But that ratio is still going to depend on the pKa. So we have this complicated relationship. Well, it's not that complicated thanks to Henderson and Hasselbalch kind of simplifying things out for us into this equation where we have the pH is equal to the pKa plus the log of the conjugate acid, the conjugate base over the conjugate acid. And we'll be, I encourage you to go and derive this, and my students will be deriving this in class. So get ready for that. It'll help you see where things come from. But for now, we're just going to use this as given. So we're going to go ahead and we're actually just going to copy and paste so we have it right where we can look at it. Okay. So in this question, we're asked, okay, what is the concentration of 150 millimolar acetic acid acetate solution at a pH of 5, and how many moles of acetate are there in the 100 milliliters of this solution? So 2 parts, we'll take them one by one, but don't worry, if you know one, you can find the other pretty easily. If you know the concentration and you know the volume, then you just have to divide by the volume and you can, voila, get the number of moles. Okay. So this is going to be the equation that we're going to be working with. So we're still going to have that situation where we have our acetic acid, and it's going to be reaching an equilibrium of acetate plus H3O plus. But this is going to be from external sources too. And so if we use Henderson-Hasselbalch, all we have to do is we have to say, okay, well, the pH is going to be 5 equals the pKa. Remember, this is going to be our 4.8 plus the log of our conjugate base over our conjugate acid. And so now we need to think about, okay, well, how can we write the conjugate acid and the conjugate base concentration in terms of some factor? If we were to solve this, and we can solve this as it is, it would give us, we can get the ratio of the conjugate base to the conjugate acid. So we can get, okay, 0.2 is equal to the log of A minus over HA. And if we were to solve this, we can get that, we take the antilog. So if we do 10 to the 0.2 is going to be equal to 1.58 is equal to our A minus over our HA. So we're going to be having about 1.5 times more of it be deprotonated than protonated. Let's think for a second. Does this make sense? If we're at a pH of 5, we have a pKa of 4.8. At a pH of 4, this means at a pH of 4.8, we would have equal amounts of the acid and the base. We're at a pH of 5. This means that we're slightly above our pKa, but not that far. So we would expect them to have similar amounts. Would we expect to have more of the acid or more of the base? If we're at a higher pH, there's fewer protons around, so we would expect that we would have more of the base form. And so this makes sense that we're getting a value that is slightly higher than the amount, it's saying there's slightly more of the base than the acid, but not dramatically. So this seems like a reasonable thing But now we want to figure out the actual amounts, not just the ratio. There are a couple of different ways we could go about solving things at this point. So one way is to take this molar ratio and convert it to a fraction. So this is a ratio of parts of our conjugate base, so parts of our acetate per part of our conjugate acid, so acetic acid. So what this is saying is we have 1.58 parts of acetate per part of acetic acid. If we want the fraction, we need to know per parts total, not per part of acid. And so the parts total is going to be equal to 1 plus our 1.58 parts of our base. So what we could do is we could find out the fraction that is A minus is going to equal 1.58 divided by 1 plus 1.58. So we're going to get 1.58 divided by 2.58, and that'll give us a value of 0.61. So that is the fraction of it that is in the deprotonated state, but we want to know the concentration. Thankfully, we know the final concentration, so all we have to do is multiply this by that final concentration. So we just take our 0.61 fraction times 0.150 molar, and that's going to give us 0.092 molar, which is the same as saying 92 millimolar. If we want to know, okay, well, how many moles of acetate are there in this solution? Well, now basically we need to take into account the volume. So remember that molarity is equal to moles per liter. And so we can just multiply it by the number of liters. We take 0.092 moles per liter times 0.1 liters is going to give us a value of 0.0092 moles, which is the same as saying 9.2 millimoles. Now I'll show you an alternative way that we could have gotten this solution. Well, we know the concentration of acetic acid and acetate. So we have the concentration of the acetic acid and the acetate. We're given that. And so this is going to be combined. So we don't know how much of this is going to be the acid and how much of it's going to be the base. But, well, now we do, because we have this ratio right here that we just figured out. And so we know that the concentration, so we know that A minus plus HA has to equal 0.150. And so we can write it in terms of just the acetate. That's what we're trying to solve here, right? So we can think about, okay, so if we set our acetate equal to X, then our HA is going to be 0.150 minus X. And because then together they would equal 0.15. And so what we could do is we could say, okay, 1.58 equals X divided by 0.150 minus X. And now we just have to plug and chug. And that's going to give you a value where our X is going to be 0.092. And I'm not worrying about like my rounding and stuff here, but the answer here would be about 0.092 molar. Okay, so now let's go ahead and let's think about if this makes sense. So every time you do an equation, every time you find an answer, I want you to stop, think about, does this make sense? Is this answer reasonable? It makes it easier to think about if things are reasonable by converting things into similar units. So we can either convert this to millimolar. So we can say that this is going to be equal to 92 millimolar, or we could think about, okay, well, we have our concentration here was 0.15 molar. And that seems reasonable given that we're talking about having about 1.5 fold. So all makes sense. This is a concentration that you could give it in either moles or millimolar. But now it's also asking us how many actual moles are there. And so in able to get this, what we're going to have to do is we're going to have to take into account the volume. So I'm just going to copy and paste this page again. Okay, so we have 0.092 molar, and we know that we have 100 mils. So what we need to do is first we need to convert the milliliters into liters. So that's going to be equal to 0.1 liters. You're going to have to get really used to converting simply between milliliters and liters and between milliliters and microliters. We're going to be using those all the time. So kind of get comfortable in your head, just quickly moving those decimal points. So we have a volume of 0.100 liters, and we have a concentration of 0.092 molar. Now, what 0.092 molar means is that we have 0.092 moles per liter. And now we're saying, okay, well, we have 100 milliliters, so that's going to be times 0.1 liter is going to equal 0.0092 moles, which is the same as saying 9.2 millimoles if we wanted to go that way. But that would be how many moles of the acetate that we actually have in the solution, because we only have that 0.1 liters. If we had a liter, we would have 92 millimoles or 0.092 moles. Okay, so that was the third kind of question. Here we're going to have to take into account the fact that we're going to have equilibrium to start with, that's then going to be changed, and now we're going to reach a new equilibrium. So it sounds like it's a totally different type of question, but really instead we just have to take into account our initial concentrations of multiple things, that your initial concentrations are coming from an original equilibrium. So our initial is going to be coming from original equilibrium. And what we're going to be doing is we're going to be adding a strong acid or a strong base and seeing how the equilibrium is shifting. What are the new concentrations? What's the new pH? So this is going to be a real practical thing, something that you might do in the lab and something that you'll be asked to do in the lab. Figure out how much the pH would change of a solution if you added a certain amount of acid or base. This is also going to help us see the point of a buffer and what happens when you're in a buffering range and outside of a buffering range. So we're going to be using this to try to kind of sketch out titration curves and show what's happening, be able to choose correct acids or bases, and know how much we might need to add in the lab to to make a certain pH solution of a buffer. Because remember that buffers have like that each acid has a specific Ka, and if you dissolve that, you'll get a certain pH, and depending on how much of it you dissolve, you can get a slightly different pH, but that's going to all be limited by the pKa, by what you put in, by the acid you put in. If you want to tip the scale more, well, then what you're going to have to do is you're going to have to add an external source of acid or a base. And so that's what we're talking about here. In order to do this, when you're adding an acid or a base, what you're going to be doing is you're typically adding the strong acid or a base. So it's all going to be dissociating. So we can think about it in terms of how many moles it's going to add pretty simply. But we can't think about things in terms of molarity very simply, because when we're adding the acid or a base, if we're adding it as a liquid, we're going to change the volume. And so we'll see another example where we're actually more practical with what we do in the lab, is instead of just adding an acid or a base to an already made buffering solution that's already at its final volume, we make it in a smaller volume, and then we adjust the pH, and then we adjust the volume, so we don't have to worry about the change in volume. But if you were to just drop some acid or base into a solution, or think about how a biochemical situation might be perturbed by the addition of an external acid or a base, well, then you don't have that luxury, and so you need to take into account the volume. And so we'll do an example where we're going to take into the account the volume, and then we'll do an example which is more like what you might be doing practically in the lab. We're going to need to figure out, okay, well, how many moles do we have in there originally? Or at least I'll show you an alternative where we can figure out kind of like the final molarity in terms of just if you were to dilute it, not considering it reacting. But when you have a strong acid or a strong base, basically all you're going to get is like a titration reaction to start with. And so all of that acid or all of that base is going to react with your weak acid or with your weak base. And the amount that can react is, well, whatever's limiting. So is it the strong, typically it's going to be like the strong acid or base you added that'll be limiting. And so basically all of it usually reacts. And then you just have to think about, okay, well, how much of it are you taking out of commission? And how much of the conjugate acid or conjugate base are you then generating? And so we'll go over an example of how this works. But it's really not as bad as it seems, thanks to that Henderson-Hasselbalch equation telling us, allowing us to kind of use that pKa value, as well as if we can find the concentrations of our conjugate acid and conjugate base using our ICE chart, and using the fact that, well, we're just subtracting a certain amount. It's this titration type reaction. We don't even need to do like solving for X. We can just figure out X based on whatever's limiting. To start by changing things into moles, or I'll show you a different way later, but basically the easiest thing to think about is to just convert it into your initial number of moles using that Henderson-Hasselbalch equation. If you know what the original pH is, you can figure out how much is of each of the conjugate acid and conjugate base are in your initial mixture. Or if you were just told what's in there and it wasn't pH adjusted at the beginning, well, then you could just figure out the initial number of moles. Now you want to think about what you're adding and predict how the equilibrium will shift. First off, we need to remember that although we've kind of been ignoring it, at least formally, there are two equilibrium that are happening here. We have our water, and it ionizes to give us our H plus, which we can think about as H3O plus, and our OH minus. And remember that when we talk about water, we typically think about water as kind of being a constant because its concentration is so high. And in fact, we have very, very little of protons or of our hydroxide present just in normal water. And even when we add an acid or something like this, it's still going to be very small quantities compared to the amount of water that we have. Because they're such small quantities, though, basically a little change in them is going to change our pH drastically. So what's going to happen is that when we have our acid-base equilibrium for our conjugate acid and conjugate base, it can easily also disrupt this water equilibrium and therefore affect the pH of the solution, which relies on the overall proton concentration and overall hydroxide concentration. So, for example, if we take our weak acid and we say that it's going to react with water, this is going to give us our conjugate base plus our H3O plus. So remember that we have this relationship in water where it's trying to reach its own equilibrium. And we have that relationship where we have that our Kw is equal to our proton concentration times our hydroxide concentration. And this Kw is basically a constant for given temp. And since it's a constant, well, it means that our H plus times our OH minus, that has to be constant as well. So if one of them increases, the other one has to decrease. And if one of them decreases, the other one has to increase. Now, the H plus can increase because you have a acid interacting with water to give you a proton. The OH minus can increase because you have a base interacting with the water to give you that hydroxide ion, which then will disrupt the balance, leading to an increase in your proton concentration. Let's look at this a little more explicitly. Now, what would happen if we added a strong acid? Well, if we add a strong acid, basically we're increasing our H3O plus. Le Chatelier's principle tells us that if we're adding a product, we're going to shift our reaction right to the left. And so basically we're going to shift towards our reactants. And what this means is that we're going to increase our amount of HA, and we're going to decrease our amount of A minus. So what we would end up with is basically we're going to get an increase in our conjugate acid and a decrease in our conjugate base. Now, you might be wondering about, okay, well, how is this affecting the water equilibrium? basically what's happening is that the protons that you add by adding that strong acid, well, they're actually also going to be interacting with your hydroxide ions that are in there. There aren't very many hydroxide ions in that water, so you're not going to be having you don't have to worry about your acid kind of being siphoned off by all those hydroxide ions. But this is going to decrease the amount of your OH minus in the solution. When this happens, basically the water has to reach its equilibrium. And remember that when we're talking about the water equilibrium, we're talking about like Kw. And so it has to adjust, which is going to mean that it's going to increase its proportion of H3O plus in order to kind of compensate for this. As a result, your pH is going to decrease when you add that strong acid. Even though we're going to consider that all of that added acid that we add is going to be consumed, you're still ending up with an increase in your proton concentration because you're disrupting the water's equilibrium. Okay, so now let's see what happens if we were to add a strong base. So if we add a strong base, we need to remember that we're not adding the conjugate base. So just like before, if we add a strong acid, we were adding basically just free protons. We weren't adding our conjugate acid. Similarly, if we add a strong base, what we're doing is we're saying, okay, we have HA plus OH minus, and now this is going to give us a reaction where basically this is going to react to give us our A minus. And in this case, it's going to give us water. So what's happening now is, well, we are deprotonating our HA, but we're not actually generating more protons. And so this is not going to increase our proton count. Instead, what it's going to do is it's actually going to decrease our pH. So what we're doing is we're adding a reactant in this case. We're going to shift things to the right. We're going to generate more of our conjugate base. And what's going to happen is that this OH minus, a bit of the OH minus that we add, it's going to, first things first, is going to react with the strongest acid in there. So it's not going to react first with your weak acid. It's going to react with those protons that are present in the solution. And then when it reacts with those, basically it's going to sop some of those up. It's going to decrease the proton concentration, and therefore you're going to get an increase in your OH minus concentration, and you're going to get an increase in your pH. So if you add strong base, then you're going to get a decrease in your proton concentration. You're going to get an increase in your OH minus concentration because these have to balance each other out to equal your Kw. And then when we added strong acid, we were increasing our H3O plus and decreasing our OH minus. And remember that when we're increasing the H3O plus, we're going to be decreasing our pH. And if we increase our OH minus, well, then that water is going to have to re-equilibrate in order to compensate, because remember that water has its own equilibrium that it needs to reach as well. What's going to happen is that our acid and base, our weak acid base equilibria are going to be intimately intertwined with the water's ionization equilibria. And so this is why we have that for a weak acid base pair, we can say that our Ka times our Kb equals our Kw. So our acid dissociation constant plus our base reaction constant when it's the base is interacting with water. And so those are going to multiply to give us our Kw, which we could also take the P versions of these and basically say pKa plus pKb equals the pKw, which is equal to 14. And so we can, this way, we can find the pKb if we know the pKa, and vice versa. And those all have to sum up to 14. Once you've predicted how things will shift and you know what you're subtracting and what you're adding, you can go ahead and set up your ice chart in moles. So remember that a strong acid or base will basically all react with the weak ones. So basically you get a titration reaction where the limiting thing, so whether it's the strong acid or strong base, or whether it's the actual amount of that acid or base you have, the weaker ones that you have in your solution, one of those is going to be limiting. And so you'll basically be adding and subtracting that limiting amount as your X. And it'll make more sense when we look at the examples, but that'll be your X. And you don't even have to go and solve crazy quadratic formulas in order to find it. Then if you need those moles, molarity, you can go ahead and just convert it back to molar by multiplying by your volume. And remember that's in liters because molar is moles per liter. And then you can find the change in pH using Henderson-Hasselbalch. And so this is going to be one that I'll want you guys to know is like if you add if you add a certain amount of acid or base to a buffer, how is that going to change the pH? And we'll also look at, well, how could we kind of like do the reverse? Like what would, like how much of an acid or a base will we need to add in order to change the pH? And so we'll look at examples of both of those, but let's start by just doing a basic example. And just note that like if you don't need to solve molarity, if you just need to solve, say, the pH using the Henderson-Hasselbalch, you can use moles in the Henderson-Hasselbalch because basically since it's just a ratio and if you're dividing by the volume to get the molarity in the first place, well, then you're dividing by the same volume on your top and your bottom. Those will cancel out. And so you can use moles or you could use molarity when you're using the Henderson-Hasselbalch. If we add 10 milliliters of 1 molar HCl to 100 milliliters of 150 millimolar acetic acid acetate, so that solution that we've been dealing with all along that we're really loving, at a pH of 5, what is the resulting pH? What is the concentration of acetate at the new equilibrium? So if in this question, we're given at a pH of 5. Now, if you see something that's saying at a pH of something, that should be a hint that you need to use the Henderson-Hasselbalch equation. And we're going to be using an ice table. We're going to be using that Henderson-Hasselbalch equation in order to figure out the original amounts of our acid, our conjugate acid and base. And then what we're going to do is we're going to figure out how things are going to change. Okay, so let's start by sketching out our initial situation. So we have an original equilibrium between our acid and our base. In this case, we're talking about an adjusted pH. So we're saying at a pH of 5, and this is what we just talked about before when we were talking about needing to use the Henderson-Hasselbalch in these types of questions. We're not actually going to have to use the Henderson-Hasselbalch here because we already used it. So we're just going to be lazy and use the value we already calculated. But that's how you would go ahead and you would find the initial concentrations. So remember that in this case, we have our acetic acid and we have our acetate and then we have our protons. And importantly, this is from our H8 dissociation and from external. So somehow you adjusted the pH, you added HCl, something like that. And so we're given this H3O plus that we have here is from all combined sources. So we don't even have to know exactly where it came from. We just have to know the value. And we can calculate that value based on the pH. So we can go, remember that relationship where we have the pH equals minus log of our H3O plus. So we can then say our H3O plus is equal to 10 to the minus pH. And then we can go ahead and we can solve this equals 10 to the minus 5.0, which is going to give us a value of 0.1234 zeros and a 1. Okay, so we're going to have this as our value. Now that's a pretty small number. Let's see how big our other numbers are, and then we'll see whether we actually need to think about this H3O plus at all. because if it's like more than an order of magnitude or so, it's not going to be, it's just kind of going to get lost in rounding. So we won't even have to think about it. But if it's bigger, we do need to think about it. So let's first just start off and think about how much of the acid and the acetate we have. And remember, at this point, we're still talking in terms of molarity. We calculated before that our acetate concentration was going to be equal to 0.093 molar. And now we need to figure out our acetic acid concentration. We know that our combined concentration of our acetic acid and our acetate is 150 millimolar or 0.15 molar. So we know that 0.150 equals our acetate, so 0.093 plus whatever our HA is. And so now we can figure out HA. And we get that HA, the concentration of our HA, is going to be equal 0.057 molar. Okay, so now we have these in terms of molarity. And now let's look and let's compare how much of the H3O plus we have compared to how much of that acid in the conjugate base we have. We can see that we have several orders of magnitude less of our H3O plus, so we're going to ignore. So we're just going to really small. So ignore here. And we're just going to take it as about take as about 0. And we're going to use this in our ICE table. But before we can put this stuff into our ICE table, first we need to convert it to moles, because remember, we're going to have to do that because our volume is going to be changing. And it's not just going to be changing a tiny amount. We're going to be changing our volume by a whole 10%. So 10 mils is 10% of 100 milliliters. And so we're going to end up with a final volume of 110 milliliters. So we'll deal with that later. We don't need to worry about that right now, but we're going to have final volume equals 10 mil plus 100 mil equals 110 mils. And because everything is like molarities in terms of liters, this is going to be equal to 0.110 liters. And so we're going to use that volume later to convert things back to molarity. But for now, we're just going to leave things we need things in terms of moles, so we don't have to worry about the volumes, because moles doesn't care how much your volume is, but concentration does. So how many moles of these do we each have? So let's think about how are we going to convert between our molarity and our numbers of moles given the volume. So we know that our molarity is moles per liter, and we want to find moles. So we have moles equals our molarity times our liters. And in this case, our liters, what we're dealing with is the starting liters, because that's where this 150 millimolar was calculated from. And so that is going to be equal to our 100 milliliters, which is equal to 0.1 liters. So what we're going to need to do is we're going to multiply this by 0.1, and we're going to multiply this by 0.1. And so what we end up with is 0.0093 moles of acetate and 0.0057 moles of our acetic acid. Now that we have the number of moles, let's go ahead and stick that into our ICE table, and then we can go ahead and we can look at how things will change. In terms of the changing, what we're doing is we're adding 10 milliliters of 0.1 molar hydrochloric acid. We need to figure out how many moles of that of H3O plus we're actually going to be adding. Because remember that the HCl is going to dissociate to give you H3O plus. And how much? Well, we have our 10 mils. So that's 0.01 liters, because remember, molarity is in moles per liter. And then we have 0.01 molar. And this is going to give us 0.001. And so this is going to be the amount of H3O plus that we add. Okay. And so now what's going to happen is that H3O plus isn't just going to hang around. It's going to react with base. So when we're dealing with a strong acid or a base, we're basically just going to have like a titration reaction. So that acid is going to react with as much acetate as it can find. And basically, if the amount of the acid that we add is less than the amount of acetate that's in there, all of our acid is going to react and we're going to have some acetate left over. If, however, we were to add more of the acid than we have of our base, then all of the base would react and we would have some acid left over. In this case, we're adding 0.001 moles worth of our H3O plus. This can then react with our acetate. In this case, the acetate has a higher concentration, and we have more moles of the acetate. So this H3O plus is all going to react, and what we're going to be left off with is it's going to subtract 0.001 from each of these. And then, but those are going, when they react, we're forming another acetic acid. So this is going to be a plus 0.001. So we have all of that is going to be going in, reacting with our acetate to form more of our acetic acid. Okay, so how is this going to affect our equilibrium? In this case, what we have is we have 0.0057 minus 0.001. Here we have 0.0093 minus 0.001. And here we have, we'll have 0 because we basically subtracted we've used up all of the acid that we added. Now, when we don't really have 0 of H3O plus, because remember we had a little bit in the beginning, but this amount that we add is going to be orders of magnitude greater than the amount that we had in the beginning, so we weren't considering it there. When we go to figure out the pH, we will be taking it into account here, but for the sake of these equations, it's not going to matter. Okay. So basically, now that we know how much we subtract, well, we have a simpler thing than we actually had before. So before we were dealing with x's, but in this case, we know the x directly, so we don't have to even use a quadratic equation. We can just do this math. So just shifting things up a bit so we can see more clearly, we can go ahead and we can do this math, and that we'll get that we have 0.0067 moles of our acetic acid, 0.0083 moles of our acetate, and kind of 0 of our H3O plus, although we'll see later that this is not going to be the value that we use to calculate the pH, because just how we were ignoring the amount of H3O plus in the water in the beginning, well, we're still going to have to consider the amount of H3O plus. And it will have changed. So there will be a change in that H3O plus value. So remember, we're adding acid. So we would expect that at the end of the day, we're going to have more protons in that water. But it's kind of complicated, and we're going to figure out the pH based on the Henderson-Hasselbalch equation using the amounts of acetic acid and acetate that we have left over, not based on the H3O plus that we have in this table. And so we'll see that at the end, how we're going to actually do this. But for now, let's figure out the molarity of these things. Remember that to find molarity, we can divide our moles by our liters. And so we have 0.110 liters. And what we can do is then we can figure out that this is going to amount to 0.061 and 0.075. And note that depending on where you round, you might get 0.076, and that's what we're going to get later. but that's going to be, these would be your values here. So alternative strategy would be, instead of calculating the molarity at the end, we can actually calculate the molarity that would be present at the new volume first, using the dilution equation C1V1 equals C2V2. So basically here, what we'd be doing is, instead of setting up the ice chart in moles and then converting it, we're going to use the C1V1 equals C2V2 to figure out what the concentrations would be at the final volume. Not taking into account any sort of actual change in their proportions or anything like this, just taking into account that final volume and kind of thinking about, like, you're instantaneously adding volume but not adding the acid, and so you kind of have to just go with it. But basically you can do the calculations based on that's there, and then not, instead of dividing it at the end, you just have to make sure that you're going to do it for all of the components of your reaction. So we can go ahead and we can set up our C1V1 equals C2V2. So our initial concentration times our initial volume equals our final concentration times our final volume. Word of caution, our V2, so our final volume, that's going to be our final volume. So that's the 110 mil. But these final concentrations aren't really the final concentrations. They're not taking into account the reacting. They're just taking into account the dilution. But if we do this, then basically what we can say is we can take the initial concentrations of each of these. And for the HCl, this is like the concentration that we're adding. It's not, remember, it's not present in the original mixture. So this will make more sense once we stick it in the table. But basically, we want to figure out what would the molarity be of these solutions when we just like initially mix them before they react. So we can get these values of 0.052 of our acetic acid, 0.085 of our acetate, and 0.0091 of our hydrochloric acid. And we can go ahead and we can plug those into our ice table. Once again, we can see that all of the H3O plus is going to react because it's going to be the limiting reagent. So for our change, what's going to happen is we're going to get minus 0.0091. We're going to get minus 0.08091. And we're going to get plus 0.0091. And now we can go ahead and we can figure out our change. Basically, we're just going to have 0.052 plus 0.0091. For our acetate, we'll have 0.085 minus 0.0091. And for our H3O plus, well, that's just all going to react, and this is going to give us 0. But note that this really isn't actually 0. It's going to be a small number. And so we're going to be able to figure out that very small number using our Henderson-Hasselbalch equation with our new amounts of our acetic acid and our acetate. Do these calculations, we can figure out the amounts of acetic acid and acetate. And remember here, we're already in molarity, so we don't have to worry about converting it afterwards. So taking into account differences in rounding, we get the same answers as before. And so now let's go ahead and let's try to figure out our pH using our Henderson-Hasselbalch equation. So if we remember that the Henderson-Hasselbalch equation tells us that the pH equals the pKa plus the log of our conjugate base over our conjugate acid. Okay, so now that we know the concentrations of our conjugate base and our conjugate acids, we can calculate the pH. So our pH is our same pKa that we've been talking about, that 4.8, plus the log of, we have that our acetate was 0.076, and we had that our acetic acid was 0.061. Now what we can do is we can go ahead and solve this equation, and we get that our pH is going to be 4.9. So does this make sense? Well, remember that we started with a pH of 5, and now we've reduced that. So yes, it does make sense. So if you were to think about it without taking into account that the pH had been adjusted at the beginning, you might be confused because you'd be like, wait, how is our pH higher? but our pH is higher, remember, because we started with the table stacked with having more of our A- than our HA. And so that's why we had to use the Henderson-Hasselbalch in the first place to get those initial concentrations. And once we knew the initial concentrations, well, now then we could figure out the final concentrations and then plug those in to get our final pH, which is 4.9. So we've gone down 0.1 in PR pH. But remember that this is a small change compared to what it would be if we didn't have any buffering capacity to begin with. So now we're going to try a different example. A couple of things are going to be different here. One is that we're adding a base instead of adding an acid. And instead of saying, okay, we're going to add this thing and see how the pH changes, we're saying, okay, we want this desired pH. How much of the base do we need to add in order to get that to our desired pH? Now, in the previous examples, we're considering volume because as we'll see in this example, you might need to add a lot of the acid or a base in order to change the pH to where you want it. So instead of just making a solution to the final volume that you want and then trying to adjust the pH, what we do in the lab is we typically make things, we dissolve the amount of the acid or of the base or of some combination of the two in less than the desired full volume. Then we adjust the pH and then we raise that volume to the final volume. And this way we don't need to worry about how much volume we added when we were adding that acid or base because we're just dealing in terms of, we're thinking in terms of the final concentrations and we'll just adjust the volume at the end to get to that final volume that we want. But by starting with a lower volume, well, now we're not going to overshoot things. So in this equation, in this example, what we're saying is how much 1 molar sodium hydroxide, so that's a strong base, remember, when you dissolve it, it's going to dissociate. So that'll be basically just adding OH minus, and that could react with our acetic acid to give us acetate. So we're saying, okay, how much of that would we need to add to bring 150 millimolar acetic acid acetate solution to a pH of 6 with a final volume of 100 milliliters? So again, you calculate it in lab and stuff, we'll calculate how you, we'll do example calculations to figure out how much you need to weigh out of your acetic acid or of acetic acid and acetate, different ways that you can do things. But we want to say in this case, okay, we have a solution of acetic acid and acetate that we dissolved. So we dissolved some acetic acid and some of it dissociated, some of it didn't. We end up with some original equilibrium. That was one of those like type 1 problems where basically we just dissolve an acid. And so we're saying that, okay, we dissolve it. So we have 150 millimolar, we want our final solution. We have 150 millimolar worth of some combination of acetic acid and acetate. So that's going to be where we have our H plus our A minus is going to be equal to 0.15. And now we want to bring it to a pH of 6. So we knew before that if we had 100 milliliters of 150 millimolar solution of acetic acid and acetate, we are going to end up with a pH of about 2.8, which is way lower than we actually want. So we're going to think we're going to need to add a lot of base, right? But how much? So to do this, we're going to take a strategy. We're going to determine the original concentration of our acetate, and this is just by using the definition of the pKa and doing one of those first types of problems that we did earlier in the video. Then we're going to determine the final concentration of acetate. And here we're talking in terms of concentrations because we're talking about, remember, we're adjusting our volume at the end, so we don't need to worry about a changing volume along the way. But we do want to know what's the final concentration of acetate that we need, and we can do this using our Henderson-Hasselbalch equation. Then we're going to go ahead and we're going to calculate the difference in the concentrations of acetate between our final that we got from the Henderson-Hasselbalch and the initial that we got just from the pKa. Now, then what we're going to do is we're going to take that difference in concentration and convert it to moles, because that's the moles that you need to basically react. And so that's in order to get that many moles of acetate, once you've already kind of let it reach equilibrium, you want to see, okay, well, how much now do I need to add from an external source in order to get it where I want? That's going to be, you find the number of moles, and then that's the number of moles of NaOH you need. And then you're going to take the NaOH, and then you're going to calculate how many mils you need by dividing that by the molarity. So let's go ahead and let's take these one by one. So let's start with our original concentration of acetate. We found out before that this was 0.0150 molar. And again, go back and previous slides, we went over that, or you could always just go back and use it using your pKa equation. Now what we're going to do is we're going to find the final concentration of acetate. And to do this, we're going to use Henderson-Hasselbalch because remember, we're adjusting the pH. So our pH, we want to get it to a pH of 6 equals our pKa, 4.8, plus log of our acetate over our acetic acid. Okay, so now we're going to have 1.2 equals log of our acetate over our acetic acid. We're not adding acetate, we're adding NaOH. So if we think about what our equation is actually, what's actually going to be going on is we're going to be having this solution where we have our acetic acid, and then it's going to be reacting with this OH minus that we put in. And this is going to give us then our acetate. And so this is the situation that we're going to be dealing with. And so we're not going to be changing the final, we're not going to be changing the total concentration of our acetic acid plus acetate. So if we think about our acetate concentration as X, well, our acetic acid concentration has to be 0.15 minus X. And so now if we're looking for A minus over HA, we can think about that as X divided by 1.15 minus X. And so now we can go ahead and we can plug that in. 1.2 equals log of our X divided by 0.15 minus X. And we end up with a number that's about 0.141 molar. Okay. An alternative way that we could have done this was similarly to how before, we find the fraction of this acetate and then multiply that by the total concentration. So in this case, basically we have our 10 to the 1.2, which we got from our pH of 6 minus the pKa of 4.8 would give us 1.2. We take 10 to the 1.2 and we get 15.8. Remember, to find the fraction, we then have to divide that by that number plus 1, taking into account that that's per 1 part of our conjugate acid. And this is going to give us a value of 0.94, which then can multiply by the concentration to get 0.14 molar. So now we want to find the change in acetate though. So now we're on number 3. So let's just clean this up a little. Okay, we want to find the change. So to find the change, we have the final. Remember, we just calculated the final 0.141 minus the initial 0.0150 is going to equal a change in the concentration of 0.126 molar. So that's our change in molarity. And we need to figure out, okay, well, how many moles is that? Because we want the final volume of 100 milliliters. That's telling us that we have 0.126 moles per liter times 0.1 liter is going to be equal to 0.0126 moles. Okay, so let's think about what this is telling us. This is telling us that the amount of OH that we need is 0.0126 moles of NaOH in order to change the pH enough that we're going to get it to the desired pH. So we need that many moles worth of the acetic acid to react after it's already reached its equilibrium. And so this is the amount that we need, this 0.0126 moles. But now we don't have moles on our bottle of NaOH, we have the concentration. And we have a concentration of 1 molar, which makes things easy. because then what we have to do is 0.0126 moles times, we just have to do, we have 1 mole per liter. So we're dividing by the concentration, and we're going to get 0.0126 liters, which is going to be, we move our decimal point 123. So that's going to be about 12.6 mils. And so you can see that if we prepared our solution to have, if we dissolved everything in 100 milliliters, and then we needed to go adjust the pH, and we had to add 12.6 milliliters of our NaOH, well, that wouldn't work out so well. So that is why we do the volume, we figure out the, do the pHing and stuff at a lower volume, and then we adjust it to the final volume. And you can always calculate ahead of time about how much you need to add. Another thing that you could do if you want to start closer to the desired pH is, instead of just dissolving the acid and letting it get where it wanted, we could have started by adding some of the acetate. So you can add like sodium acetate or something like this. And that way you're kind of tipping the scale from the beginning, rather than adding the OH and having it react with the acetic acid to make the acetate. So those are the sorts of questions that you would be expected to answer and expected to be able to calculate. I'm not going to make you do all these equations and stuff by hand. Feel free to use your Wolfram Alpha, but do be prepared to answer these questions, and we'll be doing a lot of them in the lab, as well as in class. So you'll get lots and lots of practice. Don't worry. These are just, I just wanted to give you an example of each of these, and hopefully a lot of this will be review from general chemistry. How much acetic acid and acetate would you need to dissolve to get 100 milliliters of a 50 millimolar acetic acid or acid/acetate solution at a pH of 5.5? So we're going to go ahead, and what we're going to do is we're going to figure out the molar ratio. We're going to use that to figure out the fraction, and then we could use that to figure out the concentration, which we then can multiply by the volume. So in order to do this, what we're going to say is we take our Henderson-Hasselbalch equation rearrangement, and we can basically say that's the molar ratio, our A minus over our HA, is equal to 10 to the pH minus the pKa. So that's going to equal 10 to the 5.5 minus 4.8. That's going to give us 10 to the 0.7. And if we go ahead and we plug it into our calculator, we figure out that we get 5.0. So what is this telling us? It's telling us that we have 5 parts of our conjugate base for every part of our conjugate acid. So if we want to figure out the fraction of A minus, then that's going to equal 5.0 divided by 1 plus 5.0. So that's going to equal 5.6, or about 0.83. Now what we need to do is we need to figure out the molarity. And then once we know the molarity, we can figure out the number of moles. We know what fraction of it is in this acetate form. We know the total molarity of the acetate plus acetic acid combined. So this is just going to be that number times our fraction. So times 0.050 molar. And if we do that, we get a value of 0.042. And so that's saying that this is molar. And now we just need to know our moles. So what we're going to do is we're going to take that concentration, our 0.042 moles per liter, times our volume times 0.1 liter is going to give us 0.0042 moles, which we could also write as 4.2 millimole. So that's how much we're going to need of our acetate. And what about our acetic acid? Well, there are a couple of different ways that you could go about doing this. One way is if you wanted to figure out the number of moles in the number of total moles, and then we can subtract that. So what we could do is basically we could say, okay, well, we have 0.05 molar times 0.1 liter will give us the total moles. And then we basically will get that we have 0.005 moles. And then we know that we have 0.0042 moles of our acetate. So what's left over is going to be 0.0008 moles of our acetic acid. And so then if we were to go and we would figure out, okay, well, what's the molarity of our acetic acid solution? And what's the molecular weight of our sodium acetate or whatever we're using? We can then calculate how much we'd actually have to physically add in order to get those numbers of moles. But for now, let's just see, does our number make sense? Are we above or below the pKa? We're at a pH that's above the pKa. So would we expect there to be more acid or more base? We would expect there to be more of the base form because there's fewer protons around. So we would expect that there'd be more acetate than there is acetic acid. And if we compare our numbers, we see that indeed this is the case. We have more of our acetate than our acetic acid. So this at least qualitatively seems to make sense.